Hello everyone. So before I start, I would like to thank Chair of Number Theory for supporting my presence here. So, all right, looks like some. All right. So this talk will be for a broad audience because we're all very interdisciplinary over here. So and it's also part of my doctoral work. Yeah, the theorems are peer reviewed, but I will not go into unpublished stuff. All right. What is a lattice packing? You consider a discrete subgroup such that the quotient space has finite volume. Okay, so here is some visualization happening. This is an example of what I mean by the quotient space in this green box, right? And you want to create balls centered at these lattice points such that any two of them are disjoint, all right? Okay, we call such an arrangement lattice sphere packing. It's also lattice packing, it's the same thing. And you want to talk about the packing density of such an arrangement, which is you take the fraction of the space occupied by the blue part inside the green part, which is also equal to, you take all right, which is also equal to, you take a very large ball and look at the space occupied by the balls inside the very large ball, okay? So you can also talk about, given a lattice, you can talk about the shortest vector of the lattice, which is in this picture, this orange vector. And the goal is to maximize the packing density among all lattices. So you take the volume of the ball, or you take the radius of the ball to be half of the shortest vector. All right, and then you maximize this over all possible lattices lambda, right? If you look at the quantity over there, it's the volume of the ball divided by the volume of the quotient space. This is invariant under scaling of lambda. So you have that, you can assume that your lattice has unit covolume, what is called. So we want to find, so if you assume it's unit covolume, the denominator in the packing density is 1. So you want to find this sort of a supremum, right? Okay, it says lambda is a subset of R to the D, but what I mean is like it's a discrete subgroup. And it's very classical. Each such lattice is actually nothing but a linear translate of the cubic lattice Z to the power D. In here, it's some translate of Z square inside R square. And you can use this to define a dimensional constant CD, which depends only on the dimension. So what is CD? Okay, here is some animation for 2 dimensions. Here you would expect that CD is equal to the volume of this yellow ball, but it is not, because this is not the best packing you can do. You can do this packing, which is slightly better, and this gives you the hexagonal packing in 2 dimensions. So what is CD? I repeat for you, it is the volume of the largest ball you can make, such that for some element in SLDR, there exists the lattice associated to that element of SLDR has trivial intersection with the ball. All right. So CD is between 0 and 2 to the power D. There exists a supremum. What is known about CD? We only know these finitely many cases, right? 8 and 24 has generated a lot of news, but you also know from 1 to 8 due to numerical work of Frank Valentine, etc. And for other CD, we have no clue, but we have like these fantastic lower bounds. Minkowski is very classical, goes all the way back to 19th century. Okay, so this is not an exhaustive list. So just this morning, Maxime mentioned Fassmann, and he also has some lower bounds. But yeah, but they are. We'll come back. So I'll talk about this towards the end of the talk. This is not an exhaustive list, but I would like to point to you the 2013 bound. It's the state of the art, and not all of these bounds are valid for all dimensions. Right, you only have, so the first two are valid for all dimensions, the others are selective, it works for a sparse sequence of dimensions. And the last one has the best asymptotic growth. It works for, let's say, dimension D bigger than 1000, but it has an asymptotic growth of order n log log n. The other ones are linear, and the last one is like n log log n. So let me put that in pictures. So these are some lower bounds on packing densities. The 1 to 8 are exactly known, as I said before. And there are other explicit constructions that work for other dimensions. For example, there's 16, there's 24. And these are record lower bounds. So not only do you have a lower bound, you have a lattice that demonstrates the lower bound. And you can play this game up to 72, and then there are results up to dimension 300, but then after that human imagination runs out and we have no construct. Okay, there is Fassmann. We'll come back to it, but yeah, there are no good constructions. There are so ball was the lower bound I mentioned before. It is linear. This graph suggests that CD should grow exponentially, but it's bizarre that all the lower bounds are like linear. And there is one in 2013 that's better than linear. These purple points that have just appeared now, dimension 4 and 8, these are due to Vance. So this is some comparison up to dimension 100. So now I've changed the y-axis to be CD divided by D, so all the linear bounds should look parallel to the x-axis. And I've changed the x-axis to be logarithmic scale, because now we're going to go up to dimensions 10 to the 50. So using a probabilistic argument, and in fact all of these arguments are arguments on random lattices, which is the subject of the talk. So using a probabilistic argument, Venkatesh was able to create these new purple points, and there was a new result in 21 in which we were able to extend some of these purple points. So these purple points are due to Venkatesh. As I said, they're better than linear. They grow to the order of magnitude n log log n. The new points don't grow to the same order of magnitude, but up to 10 to the 50 dimensions there are some improvements. So how does it work? The new points are based on division algebras. So there is a general philosophy in lattice packing and coding theory, which is if you're doing something with strong algebraic structures, you will get better packings. And this is a testimony to this philosophy. So the previous works are based on number fields. They were based on algebraic geometry. This is based on division algebra. And this can recover Venkatesh result from 2013, but it can also produce new bounds. So to recover Venkatesh result, you set the division ring to be a number field over Q. So it is a commutative division ring. It is in fact a field. And you set the order. So So what is the input to the theorem? You need a division ring, you need an order, you need a finite group inside that order, and it will produce this bound. So to recover this result, you put q mu n as the number field, which is also a division ring. You put the ring of integers as the order. You put the finite group as the group of torsional elements in this ring, and then it gives you Venkatesh's lower bound. But you can also cherry pick some other division rings and get more lower bounds, which was the green sequence that I showed you before. So no such sequence gives an asymptotic result strictly better than order d log d. Improvements in individual dimensions is still possible, as I showed. So here is an overview of how all this machinery works. Okay, we must prove the existence of a matrix such that the lattice associated to the matrix has trivial intersection with the ball. Okay, this is an optimization problem on a homogeneous space, which is the set of all matrices up to integer matrices. Okay, so this is a bijection of sets, but you can also call it a topological space. You can also call it a measure space. And interestingly, the measure that naturally comes on SLDR modulo SLDZ is a probability measure. It is a finite. SLDZ is a lattice in SLDR, and it has a topology of a locally compact group. It is unimodular. It is a discrete subgroup. So SLDZ is a discrete subgroup inside SLDR. The Haar measure exists, and so on. Right. As I said, it is bounded total measure. It gives us a probability space, so we can talk about random unit covolume lattices. So here I'm going to show you an experiment, and okay, we have enough time to get into this, and I know we're all hungry for lunch, but it will be fun. So consider this red ball, okay, and let f be the indicator function of this ball. The volume of the ball is given below. All right. Now consider the lattice sum function, which is a sum over all lattice points, and you do a sum f of v, right? So here in this picture, the lattice sum is 0. There is the origin, but we're not counting the origin, all right? And we can generate random lattices, so we will talk about the expected value of this random variable as we vary lambda, okay? And now this is an experiment that is going to happen in this computer on JavaScript. Right, these are some random lattices that I'm producing. Okay, and I'm trying to count what is the expected value of the lattice sum as I sample these random lattices experimentally. Okay, and I'm gonna let this run on for a while, and the point that I'm trying to make is that this number on the bottom is very close to this number on the top. Okay, so it is a random experiment. It doesn't always work, but if I take more and more points, it is going to converge to this 0.950. Right, what I'm alluding to is this very classical theorem of Siegel. It says if you have a compactly supported function, then you can play the following game. You take the lattice sums, you take the expectation value of these lattice sums. XD is your space of lattices, and if you if you take the expectation value, it's equal to the integral of f. So all of these, right, and then there is like this additional symmetry. The lattice sum is always going to be an even number, because if you have v inside your lattice intersection ball, you also have minus v inside your lattice intersection the ball. So if f is the indicator function of the ball, this tells us that there exists some lattice that intersects trivially with the ball. And this gives you that CD is greater than or equal to 2 for all dimensions D, right? If you believe the Siegel mean value theorem, this is proof that CD is greater than or equal to 2. So both this 2013 result and the division algebra lattices use this idea. What we do is, instead of this number 2 that you see, which comes from the plus minus 1 symmetry, we increase the symmetry group. The Minkowski argument is even more trivial. So he does not consider this homogeneous space of lattices. He says, given a lattice, I can construct a convex body such that, yeah, it's even more trivial. Yeah, so this Siegel is like a bit more into homogeneous spaces. Yeah, and in Venkatesh, the homogeneous space is different. It uses number fields, and this new homogeneous spaces, they come out of division algebras. And for Venkatesh, the group of symmetries is always a cyclic group, but now with this division algebra game, you can put, instead of this 2, a non-commutative group of symmetries. All right, so I glance over this because I want to get to some new stuff, but this is the theorem of Venkatesh, which is, if you look at this, the homogeneous space, it's SL2, so now it's not taking D copies, it's somehow 2 copies is sufficient, but what you're changing is the number field. So if you want to recover the 2-dimensional lattice packing version of this, you put k equal to q, right? But now here k is a number field, and kr is like the number field tensor, the real numbers tensored over q. All right, and you can, as I said, you can play the same game. This time there are, instead of plus minus 1 symmetries, you have a symmetry group of order n, and then you can construct random lattices that generate, that reach like the lower bound of n on a space of dimensions 2 phi n. So that's where the log n comes from. Yeah, so C2 phi n is greater than or equal to n. So in division algebras, we have a similar sort of homogeneous space. There it is. That is the homogeneous space, SL2 dr over SL2 O. O is an order inside a division algebra. And the way we construct this order is, it already comes with a finite subgroup, a finite non-commutative subgroup fixed inside this division ring order. Right, and this homogeneous space again has a probability measure, and you can create random lattices. You can find the expectation value, and it is equal to the integral. Yeah. Okay, and then I think, yeah, so I've already said this. So what you get is, in a space of dimensions 2 times whatever is the rank, or whatever is the dimension of D over Q, you get a lower bound that's equal to whatever is the biggest finite subgroup that can fit inside this division ring. So now, finite subgroups inside division rings apparently was like completely solved by Amitsur in 1955. And the papers that you have to read are like very terse. You have to go through theorems that look like these. And if you put enough sweat and if you put enough work, you'll figure out what are all the possible finite subgroups inside division rings. I will not go into this, but I can assure you that I've gone through all the possible finite groups, and this is the best you can do through division rings. But what I can get into is how to make these sort of results effective. So if I give you a random variable, and if I tell you in expectation it is so and so, then you can prove that there must exist an event where the value taken by the random variable was at least something. But how do you show that? How do you generate an algorithm that can construct this, that can probe the probability space and construct the instance where this random variable took the value so and so? So this is what I call controlled randomness. You have something that is happening at random, but you also want to generate instances of how this is happening. So what this requires is some sort of a discretization of your homogeneous space. Okay, so here is this discretization working for the dimension 2. So consider this lattice, which is a standard z square, and consider these lattice points mod 5. Right, so it is a disjoint union of lines. So if you consider the finite vector space fp square in this case, fp square is a disjoint union of, and if you remove the origin, then it's a disjoint union of 6 lines. So here is the colorful picture that writes f5 square remove 0 as a union of 6 lines. You could see 6 colors in this picture, and each one of those colors, they generate a lattice. And the point is that if you take larger and larger primes, these lattices become almost these lattices, in fact it's a theorem now, these lattices become equidistributed in the homogeneous space of all lattices because of the theory of Hecke equidistribution of Hecke points. These are actually what are called Hecke points in number theory. But yeah, the point is you can take this collection of lattices, and they are not yet unit covolume, so you have to scale them by a constant which depends only on p. And then you have a collection of unit covolume lattices, and you let p become bigger and bigger, and then this number of unit covolume lattices becomes bigger and bigger, and then you can ask what is the average value of the lattice sum function on such a growing collection of finite lattices. And this is also a very classical result. It's for the case that I demonstrated, it is very classical. It is a theorem of Rogers, goes all the way back to 1947, which is also when India got independent, but that's not relevant. This is not how Rogers would have written it. This is my interpretation. But the point is, what he's talking about is exactly this. It's exactly the fact that this lattice sum function behaves like a collection of really truly random points. So you can play the same game of discretizing this homogeneous space with Venkatesh result, and this was done by Moostru in 2016. And can we also do this for division rings? Yes, but you need some sort of prime ideals for division rings. Fortunately, there exists an entire theory of prime ideals for division rings. In fact, there is like this book of Victor Rayner, and if you read chapter 3 and 4, you can generate all this jargon, which is but the most important point is, what are the analogues of lines in this setup? And what's important is that if you have like a prime ideal, and if you have an order inside a division ring, you can project down and generate these matrix rings over finite fields. Yeah, and then there is this theorem from 2021, which is which is in the same number of dimensions. You can construct, using this division algebra homogeneous space, you can construct like this collection LP, which is a finite collection of lattices inside your homogeneous space. And then you can play the same game with random lattices. And all right, so now we're towards the end of the talk. So you have a finite set of random lattices that behave as good as this continuous space of all lattices, and you can play the same game about expected value of lattice intersection ball, and you can also now count the number of lattices that you've generated, and you can create an algorithm which says generate all these lattices and then go through all of them and pick one which has good packing density, and it creates an algorithm which has exponential running time, right? And it is a matter of great research. Like if you could pull that exponential running time down to polynomial running time, I mean, this is one of the big open questions of the time. Because so lattices have use in coding theory, and in their, not only they want to generate lattices with good packing efficiency, they want to generate it in polynomial time, otherwise it's not useful. And this is not quite the result that they need, but it's in the right direction. And this actually constructs algorithmically and deterministically the sequence of green points that I mentioned. And this theorem also tells you that this construction is effective. All right. And there are some details inside which I can give you on request. There are some open problems that I'll state for the community. The first question is, can you generate it in polynomial time? So Minkowski's lower bound is like known since 1890s. Can you create a lattice that attains Minkowski's lower bound in polynomial time? This is an open question. This 2021 result gives you. And this problem is called finding hay in a haystack, because you know a lot of these lattices exist. You know by your random lattice theory, but you don't know. You cannot pick one out of these random lattices. So the only thing that you can hope to do. So Fassmann has results in this. In fact, he has a survey from 90s. And he talks of all the attempts, and he doesn't quite, so he goes the other way. He starts with lattices that you can generate in polynomial time, but the lattices that he created don't quite achieve even Minkowski's lower bound. And this is an attempt in the other direction. So you start with random lattices that at least generate Minkowski's lower bound, and then you try to make the space of lattices, or the finite set of lattices, smaller and smaller. So this is part of my doctoral thesis. And then another question is, okay, you know something about the first moment of this lattice sum function. What do you know about the higher moments? If you have a probability distribution, you should not stop with one moment. You should find all the moments. And this is for the classical case, this is known due to Rogers. And for the for this number field case, it's ongoing work. We have some results on the second moment. But the third moment is still, it's ongoing, very much ongoing. And then there's another question. So I'm throwing random lattices at you. I'm giving you a finite set. I'm saying it has very good distribution, but is there equidistribution? Because I'm only considering the distributions with respect to this this lattice sum, which is it's called Siegel transform. Yeah, I'm only considering their distributions with respect to Siegel transforms, but do I have equidistribution with respect to all functions? And this is for SLDR and SLDZ, as I said before, and SLDK over SLDOK. These are theorems due to equidistribution of Hecker points. And it uses the full spectral theory of these homogeneous spaces, and it is like a very much celebrated result in arithmetic dynamics. Yeah, and for division rings it's still open, and I have no clue where to begin because the spectral theory is like non-existent. All right.
Time for question before.
Last question. What happens if you consider just two sizes of balls? Two types of balls, bigger ones and smaller ones.
Right.
If the difference of sizes is not very big, I think it will be almost the same, the results. But once the smaller ball fits into in lattices, you'll observe like a phase transition, you can get much bigger densities.
Yeah, I think, yeah, but you also need to, yeah, so you have to decide before, like, at what sides do you put the balls, you know, maybe you put at 0 mod 2 you put bigger balls, and at 1 mod 2 you put smaller balls, something like this.
Yeah, but not only two sizes.
Yes.
Just two sizes, two types of balls.
So if you fix these sides, then the homogeneous space will be one of these flag varieties. There will be different. There are like some, yeah. There are these homogeneous spaces of flags of lattices, and then you can play this game. Yeah, that's a good question.
Okay.
Yeah, but I don't know if there's like some good survey. Yeah, I haven't seen. Yeah,
I would expect a kind of phase transition when you go to smaller enough that they can go inside, so you can create a very dense lattice of big ones and then put inside. So it's whatever the randomness.
Yeah. Cool.
If not, then speak again.